1991 right now, Earth is falling, not toward the ground, toward the Sunday. Every single second, gravity is pulling this entire planet directly at our star, the same relentless pull that keeps an apple falling from a tree. The only reason we're not already there is speed. Earth is moving sideways roughly 67,000 miles per HR, fast enough that by the time gravity pulls us a little closer, we've already swept past and started curving around instead of falling straight in. An orbit isn't really the absence of falling, it is falling and missing forever in a very precise, very fragile balance. So here is the experiment. What if that balance broke? What if, for whatever reason, Earth's sideways motion simply stopped or dropped low enough that gravity finally got its way? No more missing, no more curving, just a straight line aimed directly at the center of the Sunday. How long would we actually have? What would the last weeks of a planet on a collision course with its own star actually look like? The math on this is more precise and more unsettling than you'd expect. Let's start with the number that should genuinely surprise you if Earth's orbital velocity vanished completely. Right now, this instant, Earth wouldn't spend years slowly spiraling toward the Sunday. It would take approximately 65 days. That number comes directly from orbital mechanics. An object with zero sideways velocity, sitting at Earth's current distance from the Sunday, falls inward along what is essentially a straight radial line. And the physics of that fall works out to almost exactly 2 months before impact. 2 months. That is the entire remaining lifespan of a planet once you remove the one thing that was ever keeping it in a stable orbit in the first place. For most of that fall, though, very little would look obviously different. The Sunday would grow larger in the sky day by day, almost imperceptibly at first, the way a car far down a highway looks like it is barely moving until suddenly it is very much not. The real transformation wouldn't happen gradually and evenly across those 65 days. It would happen in a violent escalating rush, concentrated almost entirely into the final stretch. But before we even get to the heat, there is a detail almost nobody accounts for. Earth's straight line fall wouldn't happen in an empty hallway. It would cross directly through the orbits of two other planets on the way down. Falling in a straight radial line from Earth's orbit to the Sunday means passing directly through the orbital distance of Venus and then deeper still through the orbital distance of Mercury before reaching the Sunday itself. That doesn't automatically mean a collision. Venus and Mercury are almost certainly going to be somewhere else in their own orbits at the exact moment Earth's path crosses theirs. The solar system's planets rarely lining up so precisely. But almost certainly isn't the same as definitely, and it is a genuinely strange thought to sit with. A doomed Earth falling silently past the distance where an entire second planet quietly orbits close enough in principle for a catastrophic, last-minute collision that would have nothing to do with the Sunday at all. If the timing happened to align, Earth wouldn't even survive to reach its own fiery ending. It would end days or even weeks earlier than expected in a sudden, planet-shattering impact with a completely unrelated world that just happened to be in the wrong place at the wrong time. Assuming no such unlikely collision, Earth would continue falling past both planets, entering a region of space already far more hostile than anything in its own orbital neighborhood. Long before the physical heat became unbearable, the sheer intensity of solar radiation itself would already be tearing at Earth's atmosphere from the outside in. The Sunday constantly emits X-rays and extreme ultraviolet radiation, and the closer Earth fell, the more of it Earth's upper atmosphere would absorb, heating and ionizing the outermost layers far faster than sunlight alone could explain. This is essentially the same mechanism scientists believe stripped away much of Mars's original atmosphere billions of years ago. Once that planet lost the protective magnetic field, it needed to hold denser air in place. Earth still has a magnetic field, but no magnetic field is designed to withstand solar radiation at a fraction of the intensity Earth would eventually be falling into. Long-distance radio communication, already fragile even in ordinary conditions, would be among the very first casualties. The ionosphere becoming so disturbed and overloaded with radiation that reliable signal transmission simply stopped working days before the ground itself became unlivable. Satellites in orbit would fail for an entirely different reason than heat directly. Intensifying radiation and increasingly frequent, ferocious solar flares would overload and fry delicate electronics far faster than any gradual temperature increase could, silently killing GPS, weather monitoring, and communication networks, while most people on the ground were still focused on the rising heat. not the invisible radiation storm already tearing through the technology they depended on. Solar radiation follows what is called the inverse square law. Cut your distance to a light source in half, and you don't just double the intensity, you quadruple it. Which means for the first several weeks of this fall, while Earth is still relatively far from the Sunday, the increase in heat and light would feel significant, but survivable, uncomfortable rather than apocalyptic. Global temperatures would begin climbing well beyond anything in Earth's recorded history within the first couple of weeks. Agriculture failing across entire continents, as growing seasons that depended on stable, moderate sunlight suddenly didn't exist anymore. But because of that squared relationship, the real horror is backloaded. Have the remaining distance again in the final days of the fall, and the intensity doesn't just double again either. It compounds brutally, each successive halving delivering a far bigger jump than the one before it. The last days of this fall wouldn't feel like a continuation of the first weeks. They would feel like an entirely different, far more violent event happening on a compressed, terrifying timescale. Long before the heat itself became the main event, though, something more specifically catastrophic would already be building: a runaway greenhouse effect, the same basic mechanism scientists believe transformed Venus from a potentially temperate ocean-bearing world into the crushing 900-degree hellscape it is today. As global temperatures rise, the oceans don't just get warmer. They begin evaporating faster, pumping more water vapor into the atmosphere. Water vapor is itself a potent greenhouse gas, so more of it in the atmosphere traps even more heat, which evaporates still more ocean water, a feedback loop that, once it truly gets going, becomes very difficult to reverse. Climate scientists studying Venus's ancient history believe this exact loop, once triggered, permanently and catastrophically stripped Venus of its oceans, boiling them away and leaving water vapor to eventually break down and escape into space entirely. Earth falling toward the Sunday would trigger the same runaway process, just compressed into weeks instead of the hundreds of millions of years it likely took to unfold on Venus. By the time Earth's oceans were fully boiling away as visible planet-wide steam, we would already be watching a preview of our own future as a second Venus, just one arriving with far less warning. Here is a detail worth pausing on because it is the kind of thing this scenario makes people expect and physics quietly refuses to deliver. As Earth falls, it doesn't fall at a constant speed. Gravity keeps accelerating it the entire way down, and by the final days of the plunge, Earth would be moving at several hundred kilometers per second, dramatically faster than its original sedate orbital speed. That sounds fast enough that you might expect relativistic effects, time dilation, mass increase, the strange physics that governs objects approaching light speed, to start becoming relevant. They would not meaningfully. Even several hundred kilometers per second is still only a small fraction of 1% of the speed of light, nowhere near the threshold, where relativity's stranger effects become physically significant. Earth's final plunge would be an extreme, violent event by every ordinary planetary standard. It would still be comfortably, unglamorously governed by the same basic Newtonian gravity that describes an apple falling from a tree, just operating at a scale and speed most falling apples never get the chance to experience. There is a subtler casualty happening at almost the exact same time, one that has nothing to do with heat directly. The moon Earth doesn't just have its own gravity. It has something called a Hill sphere, the region of space around a planet where its gravitational pull genuinely dominates over the Sundays, the invisible boundary that currently allows the moon to orbit us instead of drifting off to orbit the Sunday directly. The size of that Hill sphere isn't fixed. It depends directly on Earth's distance from the Sunday, shrinking as that distance shrinks, because the Sunday's competing gravitational pull gets stronger the closer we get to it. As Earth falls, its Hill sphere would shrink continuously, and at some point before Earth ever reaches the Sunday itself, the moon's orbit would simply fall outside the boundary of Earth's gravitational control entirely. At that point, the moon wouldn't crash into Earth, and it wouldn't keep faithfully orbiting us either. It would be gently gravitationally handed off, slipping into its own independent orbit around the Sunday, watching from a distance as the planet it had circled for over 4 billion years continued on alone. Even our oldest, most constant companion couldn't have followed us the entire way down. Somewhere in all of this, you have to wonder what humanity would actually try to do about it, given 65 days of advance warning and absolutely no historical precedent for stopping a planet from falling into its own star. The honest answer is almost nothing meaningful at the scale that would matter. Every rocket humanity has ever built exists to move a payload weighing, at most, a few hundred tons. Earth's mass is roughly 6 trillion kilograms. The idea of physically redirecting the planet itself, even slightly, sits so far beyond current or even foreseeable propulsion technology that serious physicists generally treat it as a non-starter, not a challenging engineering problem, so much as a fundamentally different scale of impossible. The only genuinely available response would be evacuation, and even that would run headfirst into brutal, unyielding limits. Existing spacecraft, launch capacity, and life support technology could realistically move a vanishingly small fraction of Earth's population off the planet in just 65 days, even under an all-out, no expense spared global effort. Mars, the most habitable alternative in the solar system, still isn't remotely ready to support large-scale permanent population, no matter how much funding or urgency you throw at the problem in 2 months. Which means the honest, uncomfortable answer is that this particular disaster, unlike an asteroid on a collision course, wouldn't really be a story about clever last-minute engineering solutions. It would be a story about a species watching its own home fall in real time, with genuine advance notice and almost no meaningful way to change the outcome. As Earth continued falling, tidal forces, the same stretching effect the moon's gravity already exerts on our oceans today, would begin acting on the entire planet with rapidly increasing intensity. Tidal force isn't just about strength of gravity. It is about the difference in gravitational pull between the near side of an object and the far side. And that difference gets dramatically stronger the closer you get to a massive body, growing far faster than gravity itself does. Long before Earth's surface temperature became survivable, this stretching effect would already be flexing the solid crust itself, not just the oceans, generating earthquakes and volcanic activity on a scale with no precedent in Earth's geological history. Every planetary body has something called a Roche limit, a minimum safe distance from a massive object, inside of which tidal forces become strong enough to overcome a smaller body's own gravity and structural strength, tearing it apart entirely. Earth would likely begin experiencing genuinely destructive tidal stress, cracking its crust and eventually pulling the planet apart into a stream of debris, before it ever actually reached the Sunday's visible surface at all. This is the detail that quietly undercuts almost every dramatic depiction of this scenario. Earth would probably never technically hit the Sunday in any clean, singular sense. It would be shredded first, torn into an elongated stream of glowing debris, which would then rain down into the sun in pieces rather than arriving as one intact planet, making a final, dramatic impact. Tiantianjian, the sun itself, deserves a specific correction here too, because it is not the kind of object Earth could actually crash into the way it might crash into another planet. The sun doesn't have a solid surface at all. What we see as its visible edge, the photosphere, is simply the layer where the sun's plasma becomes opaque enough that light can no longer easily escape from deeper inside, not a hard boundary in any physical sense. Beneath that visible layer, temperatures and pressures increase continuously and dramatically the further in you go, with no clean, solid transition anywhere to speak of. Any debris from Earth that survived long enough to reach the photosphere wouldn't strike anything resembling solid ground. It would simply be absorbed, vaporized, and eventually fused into the sun's own churning plasma. The individual atoms that once made up mountains and oceans and cities becoming, for all practical purposes, indistinguishable from the sun itself. There would be no crater, no impact flash frozen in a photograph for future civilizations to study. Just a slow, silent absorption. A planet's entire elemental inventory folding back into the star that originally forged most of those same elements, billions of years earlier inside an earlier, long-dead generation of stars. Tiantianjian stepped back from the individual mechanics for a moment, and there is a strange, quiet irony sitting underneath this entire scenario. Every heavy element in Earth's crust, every atom of iron in your blood, every trace of calcium in your bones was originally forged inside a star, most likely one considerably more massive than our own sun, in its final, violent moments before it died. That material eventually became part of the cloud of gas and dust that condensed into our sun and its surrounding planets roughly 7 billion years ago. Earth included, a planet falling into its own star wouldn't be an entirely foreign ending in the strictest chemical sense. It would be a return trip, the same atoms that were built inside a star, then briefly assembled into oceans, mountains, and the neurons currently letting you read and understand this sentence, simply completing a very long, very patient round trip back to where the raw material for all of it originally came from. Not destruction. Exactly. Recycling on a scale and timeline almost impossible to hold in your head for more than a few seconds at a time. Zan zan zan. So what would it actually look like if Earth suddenly started falling toward the sun? Not a single dramatic collision. A Liu Shu Wu Jian Day countdown, mostly quiet at first, then catastrophically compressed into its final days. As the inverse square law stopped being a gentle curve and started behaving like a cliff edge, a straight Jan line fall that would carry Earth directly through the orbits of Venus and Mercury on the way down. A near Jan miss with an entire second planet, just one more possible ending layered on top of the main one. Radiation and solar flares silently frying satellites and radio communication days before the physical heat itself became the dominant threat. A runaway greenhouse effect borrowed from Venus's own ancient history, boiling away Earth's oceans in a preview of a fate our sister planet already suffered, just billions of years earlier and immeasurably slower. A species with real advance warning and honestly almost no meaningful way to act on it. The scale of the problem sitting far outside anything current technology could actually solve in no Shu days. The moon quietly released from our gravitational grip partway through the fall, drifting into its own solitary orbit, the last of Earth's companions to let go, a crust flexed and shattered by tidal forces long before the heat itself became fatal, the planet likely torn apart before it ever touched anything resembling the sun's actual surface. And finally, no impact at all in the way we usually picture one. Just billions of years worth of assembled atoms, quietly folding back into the churning plasma they originally came from. No crater, no flash, no witness left to record the exact moment it happened. We tend to think of Earth's orbit as something solid, fixed, guaranteed. It isn't. It is a fall that has simply been missing its target for 4.5 billion consecutive years. So consistently, so reliably, that we forgot to notice we were ever falling at all.